All right, so this one is non-calculator. They give us this graph of g, so that's function g, the graph of the continuous function g, the derivative of the function f is shown above. They are going to want you to link those together at some point. It doesn't matter if you do it on part A, part B, part C, or part D, but they are going to want to see you link those together. They tell you g is the derivative of f. So f prime equals g. Write that somewhere. They're going to want you to link those together. All right, you can write it more than once, but you got to say that someplace on your paper. All right, g is piecewise linear from -5 to 3. All right, that just means that there's lines, right? It's linear and broken in pieces. And then this is the function 2x minus 4 squared is for this part. So from 3 to 6, this parabola, they give you that function. All right, if f of 1 equals 3, so that's the initial condition. Notice it doesn't start at 0, it starts at 1. It can start wherever they tell you, and it's not always 0. Find the value of f of -5. All right, so it is going to be where you started, your initial condition, which is 3, plus the displacement. And it's not from 0 to where you want to go, it's starting at 1. So it's going to be from 1 to -5. Again, these numbers can be whatever they tell you. So you just have to go with what they gave you. All right, so it's going to be 3 plus integral from 1 to -5 g of x dx. Because it says f, you would want to put f prime in there, but f prime is g of x. It's the only graph you have. It's the only function that you've got. All right, so this is going to be 3 plus, and we're going to have to do the area under the curve from 1 to -5. So here's 1, here's -5. We're going backwards. So everything is going to be opposite. So actually, this is going to be minus for this first little triangle. So this triangle right here, again, we're going backwards. So it's going to be opposite. 1/2 base times height. That would be 1/2 times 1 times 2, which would just be 1. And then still going backwards, we want to go from 1 to -5. So I've got all of this area. Now it's below sea level, but I'm going to count it as positive. It's going to be plus because again, we're going backwards. So this triangle, 1/2 base times height, that would be 1/2 times 1 times 3. That would be 3/2. And then this square right here is 3 by 3, which is 9. And you do not need to add and subtract all of that together. You don't need to simplify it down. In fact, you can leave the triangles as 1/2 base times height. You don't have to simplify anything down for the free response. You can just leave that alone. All right, letter B, evaluate integral from 1 to 6 g of x dx. Now we're going to have to do from 1 to 3 and then from 3 to 6 separately, because 1 to 3, we can just do this area under the curve. It's just going to be this square. And for 3 to 6, we have to use this function because I don't have a formula that I can find this area for. That's not like a geometric shape that I can do. All right, so integral from 1 to 6. We're going to break that into the integral from 1 to 3 plus from 3 to 6. And so you have to break that integral into those two separate parts. And actually for this one, instead of writing g of x, I should probably just go ahead and put that function. It was this right here, 2 and then x minus 4 squared dx. And you can expand that out. We've done problems like that before. I'm going to just leave this one alone because there's not much to it. And I think it's going to be easier to just look at that. All right, so first one, from 1 to 3, again, that's just this little square here. It's 2 by 2. So that area would be 4, this little square here. So that one's just 4. Plus, now this one, we need to do the antiderivative and then upper boundary minus lower boundary. This is your fundamental theorem of calculus. So pretend this was just x squared. You would have 1/3 x cubed. It's going to be the same thing, just with an x minus 4 in there. So it's going to be 2 times 1/3 x minus 4 cubed. Again, it would be 1/3 x cubed, it's just you have an x minus 4 in there. And then we need to evaluate that from 3 to 6. But again, you don't have to simplify any of it down. So you can just leave it all alone. This will be 4 plus, all right, now plugging in the 6. 6 minus 4 is 2, cubed is 8. So this would be 2/3 times 8. You know, however much or little you want to simplify that down, you can. That would be 16/3. You could leave it as 6 minus 4 cubed. You know, so go as far as you like. Right? Minus, and then the lower boundary, 3 minus 4 would be -1. So this would be 2/3 times -1 cubed. All right, so that is your answer for letter B. I'm gonna have to fold this paper over because I'm trying to hold too many things under the projector here. All right, for letter C, for -5 to 6, and that's the interval that we have this graph on. On what open intervals, if any, is the graph of f both increasing and concave up? Give a reason. I think you are going to have a lot of questions like this. You have to justify by writing a sentence. That's my prediction. I think you're going to see a lot of that. This is my favorite thing, all right? We want to find where the graph of G is increasing and concave up. Increasing means the derivative should be positive. This is the derivative graph. Remember, this is f prime. F prime is G, right? Positive, so that means above sea level. So we want it to be above the x-axis. Concave up means that it should be increasing. So we need to find where the graph we're looking at is above the x-axis and increasing. So that would be, here's the part that's above the x-axis. That would be from 0 to 1, and then also from 4 to 6. So that's your answer. So 0 to 1, and then also 4 to 6, because f prime, which is g of x, and as long as you've linked them together somewhere, you can just say one or the other, but it's safer to just say both, all right, because they equal each other. They are the same thing. Because derivative is positive and increasing there. So it's above the x-axis and it's headed up. Love questions like that. And I think you're going to get a lot of them. As long as you have this sticky note close to hand, you're going to get it. All right, D, find the x-coordinate of each point of inflection of the graph of f. Give a reason for your answer. An inflection point is a change in concavity. So that's where the derivative, which is the graph you're given, the one you're looking at, changes from increasing to decreasing or decreasing to increasing. You have to have a change. And that's how you have to write it out. So it's kind of wordy to write out. So this graph, and this point doesn't count as a point of inflection. The constant portions don't count. You have to actually change from increasing to decreasing or decreasing to increasing. And the only place that happens is right here. So there's actually only one. So x equals 4. So f of x has, I can't put all this on here. F of x has an inflection point at x equals 4 because f prime of x, which is g of x, changes from decreasing to increasing there. All right, so let me go over the points for this one. And again, C and D, I think you're going to see a lot of those. That's my prediction, is questions like those. I think you're going to see a lot of them where they have you justifying and like writing out a sentence, all right? So that was back in Unit 5. Look back at Unit 5 is where we did all of that. All right, so for part A, you get a point for setting up this integral and then a point for the answer. For part B, you get a point for separating the integrals. So splitting it at 3, making this one be 1 to 3 and this one be 3 to 6. You get a point for splitting that. And then you get a point for this antiderivative. And then you get a point for the answer. All right, part C, you get a point for stating the intervals. So 0 to 1 and 4 to 6. And then you get a point for the justification. And then same thing here, you get a point if you say the x equals 4, and then you get a point for the because part, the reason why.